Okay, the next section on page 176 is also very important, the maximum transistor ratings. Can have a look at the book there quickly to underline. We have, or you should have learned in electrical engineering and even for the diode that you've discussed in the previous chapters, that there are maximum ratings to these devices, especially power dissipation limitations, so I cannot overdrive the device, it will burn out and so forth. And this data, of course, I will get from the data sheet, the manufacturer's data sheet, as you've learned with the diodes as well. We will also have a look just now to the transistors data sheet. You should be familiar with these data sheets and how to use them, of course, and get this data from the data sheets. But if we have a look at the textbook there on page 176, maximum transistor ratings, and we read there, a BJT, like any other electronic device, has limitations on its operation. These limitations are stated in the form of maximum ratings and are normally specified on the manufacturer's data sheet. Typically, maximum ratings are given for collector to base voltage, collector to emitter voltage, emitter to base voltage, collector current, and power dissipation. But we will have a look at it just on the next few pages. Of course, like you've learned in electrical engineering, product of voltage and current, the product of VCE and IC in the case of the transistor, must not exceed the maximum power dissipation. Both VCE and IC cannot be maximum at the same time. And we've seen that, of course, on the, if I can go back here to this graph here, we've seen that on this transistor's characteristic curve. Now, remember, we had saturation point, and say, for instance, this was, or not for instance, this is the cutoff point, and I have my load line there. And they say, of course, IC max and VC, or IC and VC cannot be maximum at the same time, and I can see it according to this load line. Here I can see, say for instance, there I've got a fairly high IC, but I can see then that VC is then fairly low. And as I move along this load line, if I move down, say for instance here, I can see that the value of IC becomes much smaller, but the value of VC then increases. Okay, so they cannot be maximum at the same time. Alright, so then I can calculate. If VCE is maximum, IC can be calculated as IC is equal to PD max divided by VCE, and then if IC is maximum, VCE can be calculated by rearranging, so VC is equal to PD max divided by IC, as we can see there in the textbook. Okay, also then there's an example there. For any given transistor, a maximum power dissipation can be plotted on the collector characteristic curves as shown in figure 418a. These values are tabulated in figure 418b, and then they give you some values. These values you will normally get from the data sheet. Assume PD max is equal to 500 milliwatts, VCE max is 20 volts, IC max 50 milliamps. Those are the parameters that I need to do the calculations, of course. Then the curve shows that this particular device cannot be operated in the shaded portion of the graph. So you can see here on the graph that IC max is the limitation. IC max is the limiting, okay, I'll show you in the book. IC max is the limiting rating between points A and B, and PD max is the limiting on the graph there, and then lastly VCE max is the limiting between point C and D. Okay, so in the shaded areas it should not be operated. Anyway, if we have a look at the examples for this specific section, the bottom of the page there, firstly, just to apply this formula, a certain transistor is to be operated with a VCE of 6 volts. If its maximum power rating is 250 milliwatt, what is the most collector current that it can handle? And then I can just apply the formula to do the calculation. The example on the next page. Example there on the next page. The question asks, The transistor in figure 419 has the following maximum ratings. PD max is 800 milliwatts, VCE max 15 volts, IC max 100 milliamps. Determine the maximum value to which VCC can be adjusted without exceeding a rating. And if a rating is exceeded, which rating would be exceeded first? Firstly, the formulas that we've learned earlier, I will determine IB so that I can find IB so I can determine IC. IB by a combination of Kirchhoff's laws and Ohm's laws, VBB minus VBE over RB, 195 microamps. Then IC, which is the ratio of beta, IC divided by IB. IC is beta times IB, 19.5 milliamps. So I can see here, IC is much less than IC max, and ideally will not change with VCC. Okay, what was IC max given as? IC max was given as 100 milliamps, and IC for this specific circuit is only 19.5 milliamps. Alright, so the voltage drop across RC using Ohm's law, IC RC 19.5 volts. Now I can also determine the value of VCC when VC is equal to VCE max, it's 15 volts. So VRC then, using Kirchhoff's law, is VCC minus VCE. So VCC max is going to be VCE max plus VRC, which is 15 volts plus the 19.5 volts that we've calculated, giving me 34.5 volts. Now, VCC can be increased to 34.5 volts under the existing conditions before VCE max is exceeded. However, at this point it is not known whether or not PD max has been exceeded, so I have to go and calculate PD max. So PD max is going to be VCE max times IC. VCE max is 15 volts, IC we calculated 19.5, so it's 293. Since PD max was 800 milliwatts, remember it was given in the beginning, PD max is 800 milliwatts. So since PD max is 800 milliwatts, it is not exceeded when VCC is 34.5 volts. So VCE max is 15 volts, as 15 volts is the limiting rating in this case. If the base current is removed, causing the transistor to turn off, VCE max will be exceeded first, because the entire supply voltage, remember now, if the base current is removed, it means that the transistor goes into cutoff. The transistor now acts as a switch which is open. When the switch is open, I have to measure the voltage between VCE. What is VCE then? It is the supply voltage. What is, because the entire supply voltage, VCC, will then be dropped across the transistor. The entire voltage will be dropped, which is going to be more than that. Alright, please work through that again to make sure that you understand. Alright, while we are on power dissipation, the next section is also very important. It's called the derating of the power dissipation, or the maximum power dissipation of a transistor. Remember on the data sheet, and you should have seen that on the diode data sheet as well, for those diode devices that you've discussed. Normally these readings are taken at room temperature, which is 25 degrees Celsius. Now remember, power dissipation, it is the problem of getting rid of the heat. These devices generates heat, and if it can't get rid of the excess heat, the device will burn out. Okay, so you can imagine if a device has to operate not at 25 degrees, but at some hot place, at some furnace, at metal, next to a furnace or whatever, where it might be 50, 75 degrees or whatever, this device won't be able to dissipate the heat quick enough. So if the rating, the power dissipation rating of a specific device was, say for instance, 1 watt at 25 degrees Celsius, it won't be able to dissipate enough power so it can still do 1 watt at, say, 75 degrees Celsius. It will have to be lower now because the surrounding temperature is much hotter. So I have to go and work out the derating factor. And that is also something that I will get on the data sheet. I will see on the data sheet, as I will show you later, that the value of PD max is given at 25 degrees Celsius. And just below that it says it derates at a certain amount per degree Celsius. So the maximum power dissipation will have to be lower if the temperature is higher. Anyway, we will read that. We can read that here in the textbook as well at the bottom of page 177. Get the book moved over here. You can mark this as well. PD max is usually specified at 25 degrees Celsius. For higher temperatures, PD max is less. Data sheets often give derating factors for, not often, I think mostly, for determining PD max at any temperature above 25 degrees Celsius. For example, a derating factor of 2 milliwatt per degree Celsius indicates that the maximum power dissipation is reduced 2 milliwatt for each degree Celsius increase in the temperature above the 25 degrees Celsius. Now, so if we turn the page, we can have a look at some examples there. Example 4.7. A certain transistor has a PD max of 1 watt at 25 degrees Celsius. The derating factor is 5 milliwatt per degree Celsius. What is PD max at a temperature of 70 degrees Celsius? Alright, so, and if I don't give you these values, you will have to get them from the data sheet, but I will show you how to get them from the data sheet. So I have to go and calculate. What is the change in PD max, the delta PD max? So we've seen that it changes by 5 milliwatt per degree Celsius. So I have to go and work out at how much higher is the temperature. What's the difference between 70 and 25? You can see there it's 70 minus 25. Then multiply it by the derating factor, in this case 5 milliwatt per degree Celsius. So 70 minus 25 is going to give me 45. So 45 times that gives me a value of 225 milliwatts. So at 70 degrees, therefore PD max at 70 degrees Celsius is now the 1 watt, which is 1000 milliwatts, minus 225. Now the maximum power dissipation at 70 degrees for this device is 775 milliwatts. Alright, so always be careful. I will show you at the end of the chapter where you have to do the basic problems. If you do get a circuit diagram, it sometimes gives you the temperature at which this device has to operate. And as soon as this temperature is higher than 25 degrees Celsius, you know immediately you have to calculate the derating of the power dissipation. Alright, but we will have a look at that soon again. Okay, then we get to the transistor data sheet. We have to be able to get some of the important information from the data sheet. I think you will have to follow me in your textbooks because this doesn't display very clear. I can give you more or less an indication, but the values itself you will have to read in your textbooks. Anyway, a partial data sheet for the 2N3904 NPN transistor is shown in figure 420. Notice that the maximum collector emitter voltage is 40 volts, for instance. Anyway, let's have a look at the data sheet. Here you can see, and what is nice about a data sheet is the data sheet will give you the type number of the device. We've seen here that this specific device addresses the transistor called 2N3904, also MMBT3904, and also PZT3904. Gives you a physical picture of what the device looks like, and more importantly, if you hold the device in a certain manner, it indicates to you what is very important, because how can you use this device if you don't know this? Which terminal is collector, which is base, and which is emitter? So I can see here, for instance, for the 2N3904 specifically, the transistor normally has a flat on the one, it's flat on the one side, or there's some marking which will be indicated on the picture. If I hold it in this fashion, then I can see here if the flat bottom is at the flat part is at the bottom, I can see there that it indicates, starting from the left, what the terminals are called, collector, base, emitter, and so forth. Okay, and for the other devices as well. Okay, and normally it will give you the physical size of it as well, because if you have to go and design a circuit on a printed circuit board, you have to know what's the physical size of these devices so that you can do your design properly to get all these components fitted onto the device. Alright, then as we've seen, the very first column there, if we go and look at the data sheet there on page 179, figure 420, absolute maximum ratings is the first column there. Absolute maximum ratings, and there I can see there are values. The first one, VCEO, that's the collector emitter voltage, and then next to it there's the value, and then very important of course is also the unit. So I can see the collector to emitter voltage, and remember these are absolute maximum voltages. The value is 40 and the unit is volt. The next one is VCB, the collector base voltage is 60, unit is volts, and so forth. Emitter base voltage 6 volts, and so forth. Next one, there is the collector current continuous, 200 is the unit, the value in the unit is milliamps, and it also gives me operating and storage temperature range from minus 55 to plus 155 degrees Celsius is what this device can be stored and operated under. Right, the next section is the thermal characteristics. Now that is the important one, because we've seen the first thing there is the PD, power dissipation, and the first value that it refers to there the power dissipation, let me just see if I can get I don't think this is more clear, so let me rather go back to the computer. You'll just have to follow me there in the book. As I can see there, power dissipation, which is total device dissipation, and then you will see there are the three transistor names. It's the 2N3904, the 2N3904, and the MMB T3904. There's the one, there's the other one, and the PZT3904. And you will see that they have different power dissipations. The 2N3904 is 625, and the unit is milliwatt. The MMBT3904 is 350 milliwatt, and the PZT3904 is 1000 milliwatt, or 1 watt. Now just below the total device dissipation, you can see there's total device dissipation written, and right below that it says D-rate above 25 degrees Celsius. Now that's the important one, eh? Now for the first device, the 2N3904, I can see that the value is 5 milliwatt. And the unit, milliwatt per degree Celsius. That's important. So for each degree higher than 25 degrees, it will derate by a factor of 5 milliwatt. And for the next device, 2,8, and for the next device, 8 milliwatt. So very important, I have to get this information if the transistor has to operate at higher temperatures, that I can calculate the derated power dissipation. Right, another important thing from the data sheet that I just want to point out is on the on characteristics. Yeah, on characteristics, the first thing there, the thing that we have mentioned earlier, HFE. What is HFE? Beta DC, no? It's a DC current gain. Now what is important, you can see there on these tables are indicated minimum, maximum, and units. Okay, so it's regarding these tables down here. Okay, so what do I note for HFE? In most of these cases, they give me, remember, what influences the value of beta apart from temperature? IC, no? So IC changes there. IC at 0.1 milliamps, IC at 1 milliamp, IC at 10, 50, and 100 milliamps. And in all of these cases, most of these cases, they just give me a minimum value. They say at least, the HFE will at least be this, because we've seen earlier where we've discussed more about beta DC, that is something that the manufacturer cannot control. Okay, is the beta, the HFE of the transistor. So he can tell you it will not be less than this, but he can't tell you exactly what it is. In the case of mostly around about 10 milliamps, it will give you a minimum and a maximum value. I can see here the minimum value is 100, the maximum value is 300. Okay, so if you don't have the device in hand and you have to do a design or a calculation, I would say to take the average of the 100 and 300 to do your calculations. Okay, and normally average would be at 10 milliamps in the amplifier use as well. But what you're going to do in the lab is to determine or measure the beta value. Hopefully you know how to do that. If you're not, you're going to find out from the lab technician. He will show you how to determine the beta value of your transistor. And then you will use that value in your calculations and your design for the amplifier. Alright, so important that you will get HFE. And you will see at the end of this chapter some of the problems they ask you in the question. Do determine this and this and this and use minimum specification or maximum specification. Then I would go and look, what is the minimum HFE in this specific case? And I can see, alright, I see here the smallest number here I have is 30, for instance. Now then I will use that value. Those are the most important parameters that we use from the data sheet. But read through and see what else you can find there. And also have a look at example 4.8. It asks you to determine, or from the data sheet, to go and find specific values so that you can get some exercise with regard of using the data sheet. All right. So at this point, important again to read through the sections discussed. Work through the examples in the section, do the relevant true, false quiz, circuit action quiz, self-test questions at the end of the chapter. And very importantly, to do the relevant basic problems to this section. In this case, for this specific session is basic problems number 7 to 23. Now again, I want to stress the point. You have to work through the section first before you go and do the problems and the quizzes. If there's something that you can't do, you're going back and read again. Make sure that you understand properly, and then you go and try again. That's how the learning process takes place. No? And if there's still something that you can't do in your homework book, you can leave a space open for a specific basic problem. Then the next time we get together, you can ask this question, see if we can clarify it so that you can do the problem. I'm not going to do your homework for you. I want to make you understand how to do the problem. Then you can go and try and do the problem again.